Hello, chemistry students. This is Mr. Duffy. Welcome to our lesson for today. For today, we're going to be talking about gases and stoichiometry. Our last unit was entirely about stoichiometry. We did a lot of conversions there. And this unit is about the gas laws. And so this lesson for today combines those two together. If you remember in the last unit, we kind of just talked about, we'll get to that later. Well, this is what I'm talking about. We're going to be getting to making conversions using gas volumes in today's lesson. Let's go ahead and get started. So what we've talked about so far in our gases unit is how pressure, volume, and temperature are related according to Boyle's, Charles, and Gay-Lussac's law. So again, if we have a volume of gas, if we increase the if we increase the pressure, then the temperature has to increase to keep the volume constant. If we increase the temperature but allow the volume to change, then we have to again increase the volume. So if the temperature increases, the volume increases. That's Gay-Lussac's law, and the other one's Charles's law. So again, we've talked about how those kind of are direct relationships, and we have Boyle's law, which is the inverse relationship, and so forth. So we've already talked about those. But what we haven't talked about is what if we add the number of particles? So in the last three laws, we've kind of said the number of particles in that gas sample has to stay the same. But what if we change it? Again, what if we change it? What if we increase the number of particles? Well, if I increase the number of particles, then the volume is going to have to increase. I'm keeping the pressure the same the whole entire time, but the volume is going to have to increase. It's going to, again, think about it as a balloon. Basically, again, you're adding more air into the balloon, and the balloon's going to have to expand. So unless you do something else, the balloon's going to have to increase its volume. So that is a pretty straightforward example of the next gas law. Who came up with it? This guy, Amedeo Avogadro. You guys remember him from last chapter? The guy that came up with the mole concept? He's the same guy that came up with this law. If you add more material, if you add more particles, you add more volume. A direct relationship. Okay, so as the moles go up, the volume goes up. It gives us a direct relationship, gives us a straight line on a graph. If we plot the volume of gas over the number of moles of the gas, you can kind of see as they both increase, the line goes up as well. We get a straight linear line, which you can represent with the equation y equals mx plus b. So the volume over the number of moles equals a constant value. Okay. Right now, we're just going to say that the volume and number of moles are proportional to each other, but that's the concept. So they are proportional according to the graph. So Avogadro, again's hypothesis was that, well, this should be the same for any gas. And that's true with like Boyle's, Charles, Gay-Lussac's law as well. If we increase the volume of like the number of particles of any type of gas, that volume would increase as well. So again, he kind of applied that just like we did with the other ones, that basically if I take any sample, any balloon filled with any gas, and if I add more particles into it, the volume is going to increase. But also he said that if I have these different samples of gas and they're at the same volume, the same temperature, then they're going to have the same number of particles. So Avogadro's hypothesis, this concept that if we keep the pressure and the temperature the same, they're going to have the same volume, allows us to compare the number of particles. It allows us to make comparisons from one gas to another. Well, making relationships between one substance and another substance, especially if they have a chemical reaction, allows us to do stoichiometry. Let's take a look at that. The molar volume of a gas defines the pressures and the temperatures that Avogadro said. He said if we, again, keep it at a certain temperature, a certain pressure, we're going to have a certain volume. And that volume is going to be related to the molar mass of the gas sample. So we can use the molar mass to figure out how many moles of sample we have in it. We can figure out the volume. And he said that 1 mole of any gas at this standard temperature and pressure has a volume of 22.4 liters. This is the conversion we were kind of looking at last unit, but we never used it. Okay, so what is standard temperature and pressure? If you are at standard temperature and pressure, that is 0 degrees Celsius and 1 atmosphere. Those are pretty standard. 0 degrees Celsius is a little colder than room temperature, but it's the temperature that water freezes at. So again, that's kind of why that one was chosen. 1 atmosphere, that's typical air pressure. So that's why those were chosen as our standard temperature and pressure. If you have a volume of gas, 1 mole of any volume of gas at standard temperature and pressure, you have 22.4 liters. In other units, that would be 273 Kelvin, 101.3 kilopascals, and 760 millimeters of mercury. Those are all standard temperature pressure. That's all the same thing. Okay, let's go back to mole island now. Here we go. 1 mole equals the molar mass. We already did a whole bunch with that last unit. 1 mole equals a mole of particles. Avogadro's number of particles, 6.02 times 10 to the 23rd particles. And finally, 1 mole of gas equals 22.4 liters at standard temperature and pressure. Okay, we can use that now. We can use that conversion. So let's do it. Here's our diagram. If we're looking at our mole island diagram, the only one we weren't using before was this mole equals 22.4. And so now we're going to use that. Everything else is still applicable. We can still go to mass mountain, particle place, but now we can go to liter lagoon. That's the volume portion. Let's do a problem. We have this sample stoichiometry problem. We're going to work it out. We got an equation. What mass of water is required to react with 15.5 liters of nitrogen dioxide? Well, let me go to the board for this one. This is typical stoichiometry problem. We still have to follow the same steps for a stoichiometry problem. What we need to do is we need to balance the chemical equation first. This one's unbalanced. So we go through it, and then maybe if you kind of want to pause the video, you can balance it yourself. But it does balance with the 3, 1, 2, 1. Okay, so that balances it. A stoichiometry problem needs to be balanced to start off with. Step number 2, with any stoichiometry problem, we identify what we know and what we don't know. We're going to react 15.5 liters of nitrogen dioxide. So we're starting with 15.5 liters, and we want to know what mass of water is going to be made from that example. So how many grams of water? To do that, we're going again from liters, which is volume of a gas, to grams, mass of a product of a liquid water. So again, we're going to line up our conversion factors. 15.5 liters of NO2. There are 22.4, we're at standard temperature and pressure. Again, I should have said that in this one. Of liters of NO2 in 1 mole of NO2. That is the new stuff. So the only thing that's new from this chapter, from this unit, is this conversion. Is now we can use this conversion. So 22.4 liters in 1 mole. Between NO2 and H2O, the ratio is a 3-to-1 ratio. So there's 3 moles of NO2 for every 1 mole of water. And then finally, we want to go to grams of water. So we've got to use the molar mass of water, which is 18. If I look on the periodic table, there's 2 hydrogens and 1 oxygen. It's 18 O2 grams of H2O in 1 mole of H2O. Okay, our conversion factors are all lined up. Everything's good there. Now we just need to solve it. And so type in our calculators, 15.5 divided by 22.4 divided by 3 times 18 is going to give us a mass of 4.2 grams of water. There we go. So still a stoichiometry problem, just this conversion can now be used because of Avogadro's law. So we now have a new conversion that we can use in all of our problems. Clear this off. You might ask yourself then, okay, so I'm going to do these stoichiometry problems, but what if I'm not at standard temperature and pressure? Can I still use that 22.4 liters? The answer is no. You cannot do that yet. But we will learn how to fix it in a later lesson. Okay? So what if we're not at standard temperature pressure? Well, right now you're going to be, but later on we'll say I will get an answer for that question. So that is gases and stoichiometry, and how we can use 22.4 liters at standard temperature and pressure equals a mole of gas um, in our stoichiometry problems. So thank you for watching, and I hope this helped.